Hi everyone! In this video, we'll see how to price a risky bond paying coupons with a reduced form model for credit risk. In the previous video, we showed how to price a risky zero coupon bond with a constant default intensity model, assuming zero recovery rate. In case of default, we assumed that the bondholder will not recover any part of his initial investment. We showed that in this framework, assuming a continuous compounding, the Z-spread of the bond is equal to the default intensity of the issuer. Now, we consider a risky bond paying coupons. Coupons are paid as long as there is no default and we still assume zero recovery rate. If the bond is risk-free, by non-arbitrage, the price of the bond has the following expression. It is equal to the sum of the discounted cash flow of the bond. With continuous compounding and constant interest rate, we get this expression for the price of the risk-free bond. If we assume now that the bond is risky, in case of default, coupons are no more paid and no principal amount is returned at maturity. The sum of the discounted cash flow can be expressed as following using the indicator function equal to 1 if there is no default before t and 0 otherwise. With continuous compounding and constant interest rates, we get this expression. The price of the risky bond is the expectation of the sum of the discounted cash flows. The expectation of the indicator function at t is nothing else than the survival probability, the probability that there is no default before t. It is equal to the exponential of minus lambda times t with a constant default intensity model. And if we calculate the integral term, we obtain this expression, which can be rewritten like this. We see that the price of the risky bond is higher than 100 if the coupon of the bond divided by 100 is strictly higher than the sum of the risk-free interest rate R and the default intensity lambda. If it is strictly below, the price will be lower than 100, and the bond will be at par if the two are equal. The last term is the risky duration. It is the integral of the discount factor times the survival probability between 0 and t. The risky duration is lower than the non-risky duration as it includes as well the risk of default before the expiry of the bond. The higher the default risk of the bond, the lower the risky duration. When lambda tends to infinity, meaning that the default probability tends to 1, the risky duration tends to 0 and the bond price as well. We illustrate it here with a Python code. When lambda is equal to 0, the risky duration is equal to the non-risky one, while it tends to 0 when the default intensity is very high. In this example, with a coupon equal to 6% and a risk-free interest rate equal to 5%, we see that the bond price is above par when lambda is small, below 1%. The bond price tends to 0 when lambda is very large, meaning a very high default risk. As a reminder, the Z-spread is a spread that needs to be added to the risk-free rate to obtain the price of the risky bond. It is the additional compensation asked by investors for taking the credit risk. With continuous compounding, we obtain this relationship between the bond price and the Z-spread, which can be rewritten like this. And if we compare it with the expression of the bond price as a function of the default intensity lambda, assuming that there is no recovery rate in case of default, we see that the Z-spread Z is equal to the default intensity lambda. In the next video, we will see that this is no more true if the recovery rate is not null. Thank you for your time.